All right, so as we finish up this chapter, these are literally the last derivatives you have to learn. Okay, the ones that are in this lesson. Okay, after that, you have learned to take the derivative of every single kind of function that man has, as of yet, come up with. All right, so you know polynomials, you know trig, you know inverse trig, you know how to do rational functions, you know how to do square roots. We just have to cover this last bless you. All right, so let's get her done. Okay, so an exponential. By definition, an exponential is a to the u. A has to be a constant in order to make it an exponential. One of the most common exponentials is e to the u because e is a constant. Do you guys know the value of e approximately? 2.7 something-ish, okay? As long as you're in the ballpark of 2.7, you're fine, as long as you know it's less than pi. Okay, so pi is slightly greater than 3, e is slightly less than 3. As long as you have a working knowledge of generally what that is, that'll be helpful. That is the most famous, okay? But an exponential is anything where that has to be a constant. If it's not a constant, it's not an exponential. Okay, now the constant can look weird. The constant can be the square root of 17, but that's still a constant. Okay, sometimes that throws people off because they expect it only works on 10s and 2s and 5s and nice numbers. But as long as it's a constant, it's considered an exponential. Okay, so let's review just the power rule. Okay, so if it's not a constant, okay, we all know that x is not a constant. It's called a variable, okay, which is completely opposite of a constant. A variable, the root word in there is to vary or to change, and so it is not a constant value. All right, so we have hit that. Come on, nope, I ruined it. And we know that it's in parentheses x to the n minus 1, so move the power down, decrease the power, and now by virtue of the chain rule, we know that there's always, with parentheses, an additional derivative, and in this case with x, it's just 1. All right, so that works on the following two problems because the variable is positioned in the base. All right, so we apply the power rule, we pull that to the front. So my derivative y prime, 0.85 pulled to the front. I decrease by subtracting 1, which makes that a negative decimal value. The inside remains unchanged. And then the chain rule would require me to do an additional derivative, which would be multiplied by the number 3. Okay, in the second example, the variable is still part of the base because we understand that the implication here is that sine of 2x is inside a nested set of parentheses and pi is the power. So this is still considered a power function because the variable is part of that trapped base inside the parentheses. And so the rule is still the same. We still pull the pi to the front and we subtract 1. So my derivative will be pi in front and pi minus 1. Okay, even though pi is an irrational number, so 3.14159, now it's going to be 2.14159 because we've just subtracted 1 from it, but it's just better to write pi minus 1. And then the inside remains unchanged. And then we tack onto that the derivative of cosine, and that inside remains unchanged. And then we finally finish with the derivative of 2. And then your final answer, you'd put that in a preferable order, which always has 2 pi in the front. And then I would probably put my sine of 2x next and have the parentheses indicating that the power is affecting that, and then finish it up with cos 2x at the end. But equivalent answers are okay. All right, so that's by virtue of review. So now we're going to move on to exponential. So if the base is numerical, okay, again, I can't emphasize that enough, that this rule applies when the a here has to be a constant. Okay, it must be a constant. If it's not, then you treat it as a power rule. All right, so here's the derivative. You copy it, okay, a to the u, and then there's implied multiplication. So it literally copies itself. It's like a copy paste. If it started out as a to the u, the derivative starts with a to the u. And then you do implied multiplication, and you always multiply by the logarithm of what a was. So if it was a 5, then we'd have natural log 5. If it was a pi, we'd have natural log pi. And then there's an implied chain rule multiplication where you multiply by the derivative of the thing where the x is. Okay, that's the plug and chug rule. There's 3 parts to it. Part 1, part 2, part 3. Okay, and just do them in order and then clean up what you have. So if that's the case, that should work on E, because E follows that model. All right, so the derivative of E with u as its power, what does it start with? U. E with u as its power. That's how it starts. And then, okay, right, the natural log of E, okay? And then, what would be next? Okay, no, not close, okay? It's going to be, we're not going to pull the powers down or anything like that, okay? We just do the derivative of what's up there. So that would be derivative u with respect to the variable x, okay? Yeah, now if it's dx, it'll be 1, okay? If it's du dx and u is something you know how to take the derivative of already, then you will take the derivative of it, but you should. So I'll show you an example. But what is the natural log of e always going to simplify to? 1. All right, so this would simplify to e to the u and then times du dx. So it's going to look like there's no logarithm, but we know that there really was a logarithm there. It's just happened to be simplified to 1. All right, so let's plug and chug this. Okay, what about this problem makes it an exponential? Can you identify it?
There's a constant.
Okay, the number 3. Okay, that's what makes it an exponential. Okay, because the x is part of the power. It's the 3 that makes it an exponential. So the derivative will have 3 parts to it. It's itself. And then the second part is going to be what? Natural log 3 that's what made it the exponential. And then the last part would be apply the derivative rules to whatever the power is. So I'd have 2x. Okay, and that's it. Now, there's nothing else I can do to simplify that other than maybe rearrange. So most often you'll see the 2x in the front, and you'd see the natural log 3 next. And then you would see the 3 to the x squared tacked on the end. A lot of times the natural log of 3 is put in parentheses to protect it from getting incorrectly attached to the 3x squared. Let me show you what happens sometimes if people get in a hurry and they make careless mistakes. Is I might see this as an answer. I might see the natural log of 9x squared. Okay, where people are like combined, they see 3 times 3 and they think they're supposed to multiply those two together. That's not 3 times 3. That's the natural log of 3 times a separate 3 to the x squared. So because this is wrong, somebody who wants to be intentionally careful about what they're doing might use parentheses there and say, okay, I want the natural log of 3 and I want that to be in parentheses so that I'm not tempted to multiply those two together. But it happens more often than you would know where people multiply the two together. Okay, let's try another one. Okay. All right, Stephen, on this one, what about it makes it exponential?
The 5?
Yep, the 5 is what makes it exponential. So the derivative of this is going to start with itself. And then the next piece is going to be that ln 5, because that's the part that made it exponential. If you want to put that in parentheses right away, you can. Then I tackle the derivative of the cotangent. Okay, we remember what the derivative of cotangent is? Okay, negative cosecant squared. And what goes in that parentheses? 3x. Okay, and then because there's still parentheses, I have the 3 on the end. Okay, can that 3 on the end be combined with any of the other terms? No. No, that 3 at the end doesn't multiply by the 3 to make 9. It doesn't multiply by any of the 5s to make 15. That is the only constant 3 there is. So if I'm just going to put this in the right order, I would lead with negative 3. It's a constant. What else is constant there? Cosecant squared is not constant because it has a variable in it. The natural log of 5 is the only other constant. So I would do that one next. Okay, so 3 ln 5. The other two are the variable pieces, and the order of those doesn't really matter. So you could do 5 to the cotangent of 3x and then times the cosecant squared of 3x. There is no preferential treatment to how you write that, but typically you would lead with all the constants. Yeah?
Like, would it matter on the test if we put it in different order?
Yeah, the only thing that would matter is if you did negative natural log of 5 times 3, and like you put it in that order, and then also proceeded to say the natural log of 15. So there is nothing wrong with the negative natural log of 5 times 3 written that way, but it's always better to be clear that the 5 and the 3 are not connected in any way. All right, let's try another one. Okay. All right, Julie, what about this makes it exponential? Not the 3. The 3 is a cube, and that's not what makes this an exponential. Okay, so we have to think about what makes this an exponential. Okay, Nick, what do you think? The E is what makes it an exponential. E is a constant, and it's acting as the base here. So our derivative would start with e to the x cubed. It starts with that same problem. Okay, then it's the natural log of what made it exponential, so the natural log of e. And then simplified to be 3x squared. I would take a half point off if you never simplified the natural log of e. Okay, so the natural log of e does have the value of 1. And so you would want to probably say the 3x squared is first and then e to the x cubed. But you could also say that in a different order, but I would expect you to simplify the natural log of 3 to be 1. Okay, any questions on that one? It's not going to be this part where people make the mistake unless they forget chain rule. But it's usually not there. It's usually any simplification algebra is where people are going to get caught up. All right. Now we can still do the same things we were doing before. We can find a tangent line, which means we need to evaluate a point and we need to evaluate a slope. So my point will be using y equals e to the sine 2x. My slope evaluation will be using y prime equals and then the derivative of that. Or is there anybody who wants to try this derivative? Rain, how about it?
E to the sine 2x times ln
Okay.
times cos 2x times 2.
Okay, times the cosine of 2x, and then times 2. That's how we say it in our head, right? And then it comes out. Okay, good. So we have a point, we have a function to work with, and we have a derivative to work with. So we should be able to find our point value and our slope value. So to find our point value, we'll go back to the y equals equation. I'll plug pi in there. That'll e to the sine of 2, and then pi gets plugged in. All right, so what is the sine of 2 pi? It is. So this is not 0, it's e to the 0, okay? Now, e to the 0 happens to be 1. Okay, now if I plug this in my pi into my next equation, so I'll have e to the sine of 2 pi, and then the natural log of e, which will be 1, and then the cosine of 2 pi, and then 2. So what is the sine of 2 pi? The sine of 2 pi. No, the sine of 2 pi is 0. So this is e to the 0. The natural log of e is 1. The cosine of 2 pi is 1 and then times 2. So we've got e to the 0 times 1 times 1 times 1, which is 1 times 1 times 1, which is 2. All right, so there's my slope. So my tangent line would be y minus the point value of 1, the slope value of 2, and the x value of pi.
You can graph that, please.
You could graph it.
My big brain just went.
Do we even remember why we do tangent lines?
Yeah.
Okay. So I'll get you, Chloe, just a minute. All right, so e to the sine 2x is a function that passes what test?
The horizontal.
Vertical line test, right? Okay, so e looks like this, but if you throw the sine 2x in it, because sine has what kind of behavior? Okay, and so then e to the sine 2x is going to be like oscillating as it goes up. All right, but what does a tangent line do? It finds the point that you're looking at and just sort of skims right off of it, right? So if our point is right here, it's going to skim right off of that. It is the instant. It's going to, okay, so that's what that,
So why do we do
okay?
that?
The y is coming in chapter 4 of what we use that for.
Okay.
Okay, but we're learning the how right now. We're getting really good at the how. But if it was right there, then maybe it would be, more steep like that. Or if it was in one of the, it was here, then it's going to be more like that because it's going in a down direction. Okay, Chloe.
I was wondering, would it ever be like the sign of like not too high, something that was harder that we need our calculator for? Or
So yeah, if it was not on the unit circle, then you'd have your calculator.
okay. Or
The only ones you're going to get are ones that are on the unit circle. So pi halves, pi thirds, pi fourths, pi sixths.
Yeah, or like even if it was that, and then like the sign of it was like, it wasn't 0. Would
Oh.
you know what e to the power or something?
No, so you would leave, so say it turned out to be like rad 2 over 2,
Yeah.
right? So you would just leave it e to the rad 2 over 2. You don't evaluate it, you just leave it. Yeah, it's only e to the 0, e to the 1, and e to the negative 1 that are, so e to the 0 we know is 1, e to the 1 we know is e to the negative 1, what's that? 1 over e. Those are really the only ones you can do anything with. All right. Okay, so just to finish this up. Wait.
times 0. So
What? Okay. So how do you take, what rule do you use for y equals 4 to the 3? Okay. All right. We don't use the exponential rule because the exponential rule requires a constant base only, not a constant power. We don't use the power rule because the power rule requires a variable base, which I also don't have. Okay, so both things are constant. The 4 is constant, the 3 is constant. Okay, and the derivative of any constant, no matter what it looks like, is what? 0. Okay, this is the constant rule. And the derivative of that is always 0. Okay, what rule do I use for the second one, the middle one? That's the power rule. Okay, because only the power is constant, the variable is in the base, and so that would be 3x squared. And it's only the last one that we use the exponential rule on. And what makes it exponential is the 4. And so its derivative will be 4 to the x times the natural log of 4 times dx dx, which is going to be 1. Now you may look at the back of the book and see this answer, 2 ln 2 4 to the x. Okay, So that comes back to, do you remember what to do with an ln of 4? Okay. All right. 4 is a perfect square, just like 9 or 16 or 25. Okay, so you learned back in Ham that 4 is written as 2 squared. And in logarithms, if you have a power, you can always pull the power to the front. Now, that's not the same kind of pulling the power to the front as a derivative. This is just a logarithmic property that says that you can pull this 2 to the front and then have 2 ln 2. So I just wanted you to know, if you see that, that's equivalent answer. Okay? So in other words, if you saw, if I gave you like ln 125, okay? Well, what is 125? 5 cubed. And so you could write that as 3 ln 5. Okay, those are equivalent. Okay? Well, it sometimes will allow you to reduce things, right? It's going to be in it. So all I'm saying is equivalent answers are fine, but if you're looking to match a multiple choice, you'll need to know how to match it.
So that'd be
Okay?
natural log 2 times 4 dx.
Yes.